Chapter 6, Electron Configuration and the Periodic Table. Welcome back to Chemistry 101. Today, we're exploring Chapter 6, Electron Configuration and the Periodic Table. This chapter covers the arrangement of electrons in atoms, the nature of electromagnetic radiation, atomic spectroscopy, and the principles that explain the structure of the periodic table. Understanding these concepts is crucial for mastering high school, honors, and AP chemistry. Let's dive in. Electromagnetic radiation. Introduction to electromagnetic radiation. Electromagnetic radiation refers to energy that travels through space in the form of waves. This includes a wide range of types, such as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. All these forms of radiation differ in wavelength and frequency but travel at the same speed in a vacuum, the speed of light, which is approximately 3.00 times 10 to the power of 8 meters per second. Key concepts. Wavelength, lambda, the distance between two consecutive peaks or troughs in a wave. Frequency, nu, the number of wave cycles that pass a point per second, measured in Hz Hz. Speed of light, c, the speed at which light travels in a vacuum, given by c equals lambda times v, or wavelength times frequency. Energy of a photon, the energy associated with a photon, a particle of light, is related to its frequency. E equals h times nu. Where E is the energy, h is Planck's constant, 6.626 by 10 to the negative 34 power Js. Atomic spectroscopy and energy levels. Atomic spectroscopy. Atomic spectroscopy involves studying the light emitted or absorbed by electrons as they move between energy levels in an atom. When electrons absorb energy, they jump to higher energy levels, excited states. When they return to lower energy levels, ground states, they emit energy in the form of light, which corresponds to specific wavelengths. Key concepts. Ground state, the lowest energy state of an atom where all electrons are in the lowest possible energy levels. Excited state, a higher energy state of an atom where one or more electrons have absorbed energy and moved to a higher energy level. Emission spectrum, the spectrum of light released by electrons as they drop from higher energy levels to lower ones, producing discrete lines of specific wavelengths. Absorption spectrum, the spectrum of light absorbed by electrons as they move from lower to higher energy levels. Bohr model of the atom. The Bohr model describes electrons as moving in fixed orbits around the nucleus with quantized energy levels. Although this model has been superseded by quantum mechanics, it introduced the idea that electrons occupy specific energy levels, which is key to understanding atomic spectra. The description of electrons in atoms. Quantum mechanical model. The quantum mechanical model is the current model of the atom that describes electrons as existing in orbitals, regions of space where there is a high probability of finding an electron. Unlike the fixed orbits in the Bohr model, orbitals are defined by wave functions that describe the electron's behavior as both a particle and a wave. Key concepts. Orbitals, regions in an atom where there is a high probability of finding electrons. They are described by quantum numbers. Principal quantum number, n, indicates the main energy level occupied by the electron. Angular momentum quantum number, L, indicates the shape of the orbital, s, p, d, f. Magnetic quantum number, m, indicates the orientation of the orbital in space. Spin quantum number, s, indicates the spin direction of the electron. Electron configuration. Electron configuration describes the arrangement of electrons in an atom. Electrons fill orbitals in a specific order based on the energy levels, following the Aufbau principle, Pauli exclusion principle, and Hund's rule. Aufbau principle, electrons occupy the lowest energy orbitals first. Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum numbers. Hund's rule, electrons will occupy degenerate orbitals singly as much as possible before pairing up. Example of electron configuration. Carbon, C, 1s superscript 2 2s superscript 2 2p superscript 2. Oxygen, O, 1s superscript 2 2s superscript 2 2p. These configurations indicate the distribution of electrons among the orbitals of an atom, which determines its chemical properties. Multi-electron atoms, the Aufbau principle, in the periodic table. Multi-electron atoms. In multi-electron atoms, electron-electron interactions cause splitting of energy levels, leading to a more complex energy level diagram than that of hydrogen. The energy levels in multi-electron atoms are influenced by both the nuclear charge and the repulsion between electrons. Aufbau principle and periodic table. The Aufbau principle helps explain the order in which orbitals are filled, leading to the periodic arrangement of elements. The periodic table is organized according to increasing atomic number, and the structure reflects the filling of electron orbitals. Periodic trends. Atomic radius decreases across a period, left to right, due to increasing nuclear charge pulling electrons closer, and increases down a group due to additional electron shells. Ionization energy increases across a period as nuclear charge increases and decreases down a group due to increasing distance between the nucleus and the outermost electron. Electronegativity increases across a period and decreases down a group, following the same trend as ionization energy. Periodic law, trends, and atomic properties. Periodic law. The periodic law states that when elements are arranged in order of increasing atomic number, elements with similar chemical and physical properties appear at regular intervals. This periodicity is due to the repetition of similar electron configurations in the outer shells of atoms. Periodic trends and their implications. Understanding periodic trends is essential for predicting the behavior of elements in chemical reactions. Atomic radius influences the size of atoms and the strength of bonding interactions. Ionization energy affects the ability of an atom to lose an electron and form cations. Electronegativity determines the type of bonds, ionic or covalent, an atom will form and how it will interact with other atoms. Examples of periodic trends in action. Metals generally have larger atomic radii, lower ionization energies, and lower electronegativities, making them good conductors of electricity and heat, and often forming cations in reactions. Nonmetals have smaller atomic radii, higher ionization energies, and higher electronegativities, making them more likely to gain electrons and form anions or share electrons in covalent bonds. Conclusion. Today, we covered the fundamental concepts of electron configuration and the periodic table, including electromagnetic radiation, atomic spectroscopy, the quantum mechanical model of the atom, and periodic trends. These topics are essential for understanding the structure and behavior of atoms, which in turn explains the properties and reactivity of elements. Mastery of these concepts prepares you for more advanced studies in chemistry and related fields. Thank you for joining today's lesson on Chapter 6, Electron Configuration and the Periodic Table. Stay tuned for our next chapter, where we will explore covalent bonding and molecular structures. Don't forget to like, subscribe, and share this video. Until next time. Dr. Siegfried Howell.